So we are pleased to welcome Ari Jovinelly from Brown that is going to speak about free curves in singular varieties.
Thank you. And thank you for inviting me to give a talk. It's my pleasure to come here. So this talk I'm going to be speaking mostly about, varieties and curves in them. In particular, I'm going to focus on phono varieties. And so I wanted to give a brief blurb about why we're going to focus on varieties that are phono. And that's mostly because, there's this thing by the MMP that you can try and reduce a variety into different parts, right? Pieces or parts, right? And the three types of parts you get out of it are phono varieties, right? Calabi-Yau type varieties and general type varieties, right? And so phono varieties are like the positive bits, right? They're the bits that have like nice combinatorial structures. There's a lot of toric phono varieties, right? And they're the pieces that we try to like understand sort of the best. We can hope to understand the best. And so today I'm going to talk to you about some properties that we don't yet understand, but we're still trying to, okay? So maybe I should start with the definition, right? What do I mean by a phono variety? So a normal projective variety X is phono if the anti-canonical divisor which I will denote throughout this talk by negative kx, is ample and Q-cardier. Right? So if you want, you can just forget about this last condition. What I mean is that there's a Weil divisor associated to the anti-canonical divisor, right? I look at the smooth locus. I have a canonical line, or I have a canonical line bundle. I can associate a divisor class to this on the smooth locus, extend it to the entire variety, look at that Weil divisor and say, I want some tensor power of this, the sheaf corresponding to this to be a line bundle that's very ample, okay? All right. And so what are some examples, right? Low degree hypersurfaces in Pn, right? So a hypersurface of degree less than or equal to n in Pn is a phono variety when it's normal, right? Some other products of phono varieties or blowups of projective space or other phono varieties are frequently phono. Toric varieties with especially nice structure, again, phono. If you're very familiar with toric varieties, what you should think about is phono varieties are, slight, or not so slight, but, sort of toric geometry, toric varieties with less structure. Maybe their Cox ring is still finitely generated, right? But it may not be free algebra, right? If I remember that correctly. I'm not super familiar with toric varieties, right? So there may be relations, okay? All right, great. So it's a Mori dream space, if that helps. So what did Mori, right, sort of realize about these varieties? Or maybe to give a little bit more history, why are they called phono varieties? So I'm going to be talking about Mori. They're called phono because they were sort of investigated first by Giuseppe Fano in the early 20th century to come up with a counterexample to this rationality conjecture that every unirational variety would be rational itself, right? They proved that this is true for surfaces over C. And then Fano was like, hey, I don't think this should be true for threefolds, and looked into a cubic threefold, right? A cubic hypersurface in P4. And it turns out this isn't rational, but it is unirational. These are two different measures of sort of rationality. What? It means that it is dominated by projective space. There's a generically finite map from projective space to it that may not be a birational map, right? It may have like fibers of degree larger than 1, but it is still dominated by projective space. Does that? Okay. All right. So great. So eventually, through like much of the 20th century, it was shown that this is a counterexample, but a lot of work went into it. And so people started understanding phono varieties a little bit better throughout the 20th century. And finally, Mori came around and sort of revolutionized how we think about them, right? What Mori realized is that many geometric properties that people had begun to study about phono varieties of x, the phono x, depend on the behavior of rational curves it contains. Right, so what do I mean by many properties, right? Among these are, well, its behavior under the MMP, if you're familiar with this. Its fundamental group, information about rational curves on the variety can tell you information about its fundamental group. And sort of boundedness and moduli that people have established. I'll touch on that a little bit in a second. Okay. So what do I mean rational curves? Maybe this is, another key definition in my talk. So why don't I give it ample space on a board? Definition. A rational curve on X is a non-constant map from P1 into X. Okay, so this is a geometrically rational curve, if you will, right? And we're further going to say, right, that a map or rational curve f from P1 to X is called an R-free rational curve if, so this is for R greater than or equal to 0, if 1, the image of the map lies in the smooth locus of X. Right? So I want to avoid sort of bad singularities in X. Okay? And 2, well, if it maps into the smooth locus of X, then the pullback of the tangent bundle will be a vector bundle, right? And any vector bundle on P1 decomposes into a direct sum of line bundles O of AI, right? And I want this isomorphism, or I want this decomposition to be, I want, the pullback to be a direct sum of line bundles where the degree of every line bundle is at least R. Okay, this is what it means for the curve to be R-free. And so some nomenclature. So free, if you just say free, this means a zero-free curve. So the pullback of the tangent bundle is globally generated, right? And very free means one free. So the pullback of the tangent bundle is ample. Okay? And there are some geometric consequences to this, restriction, this definition of free that I'll get into a little later in the talk. And maybe I should draw a picture as well to help visualize. So maybe I have some singularities on X. This is big X, the little x's are singularities. And I want my rational curve to miss all of them. Okay. All right. So what are some of the things that I'm saying, vaguely? Maury said geometric properties of X depend on the behavior of rational curves it contains. Well, so I have the following theorem. This is by Kolar, Maury, and Miyaoka. From the 90s. So what they realized is that one, smooth phonovarieties contain very free rational curves. Okay, so these phonovarieties always, or smooth phonovarieties always have these very free rational curves. And in particular, they showed that if you, fix the dimension, then you can bound the degree of a rational curve that you can find a rational curve of like a very free rational curve of bounded degree. So I'll just write of bounded negative kx degree. in fixed dimension of X, right? Okay. And so one of their, their first corollary of this, or a major corollary of this, was the first proof of the following fact. Smooth phonovarieties form bounded families. So in each dimension. So maybe I should, of a fixed dimension form a bounded family. What I mean by this is there's some quasi-projective scheme that will parameterize all phonovarieties of a fixed dimension, all smooth phonovarieties of a fixed dimension, right? That there's not infinitely many components of this scheme, right? A priori, a general type variety, right, of a fixed dimension, you can find infinitely many of these types, right? Or infinitely many general type varieties of a fixed dimension, right? There's no moduli space of general type varieties that'll have quasi-projective structure, but there is for phonovarieties. So there's some hope of studying them by looking at different deformation types individually, maybe. Yeah? Why 2 is good? Yeah. Sure. So deformations, it comes from trying to look at deformations of a curve. And so if I want to understand how my curves move in my variety, right, then what I want is like, an infinitesimal deformation of the curve, right? I want to see how it will deform in a small epsilon neighborhood, right? And so what's a way of giving an infinitesimal deformation of a curve? It's to give a global section of a pullback of a tangent bundle, right? It's a choice of a tangent direction at every single point, right? And so once I have that my pullback of the tangent bundle is globally generated, what this means is that I can move the curve in any which way, right? That if I fix a point on the curve and I want to move that point, somewhere else in X, I can move it in any which direction I want, right? And so that's why it sort of means free, right? It's not constrained to lie in any subvariety, right? I can move it around kind of as much as I want, right? And it just turns out that when you narrow in on the deformation theory a little bit, this free property really gives you sort of everything you want, right? And that's a great lead-in question because the next remark, does that answer your question? Okay.
So it basically means you can move an infinitesimal, also just really move it.
Yes, that's another stipulation that for rational curves, when the obstruction space is sort of, is going to be the H1 of the pullback of the tangent bundle, right? And so when you're globally generated, this vanishes, and so you not only move it infinitesimally, but you actually get an honest deformation, right? Great question. These will come up later in the talk, so thank you. Okay, so the remark is, from the conversation we just had, maybe that, how did they use fact 1 to prove fact 2? Well, it's through some of the nice geometry that we just talked about, right? And so the remark is that free rational curves have good deformation properties. Right? Think about lines in PN, right? Maybe, or conics in PN, right? But here, it's essential that the image of the map lie inside X smooth, right? We're really using this condition quite a bit when we say that these free rational curves have good deformation properties, right? Because, well, first, how do I even state a condition like this, right, if I don't lie in the smooth locus? My pullback of the tangent bundle probably won't be a vector bundle at this point, right? But 2, frequently when I, have a curve that meets a singularity, right, think about like a line in a cone, right? It won't move to, it won't move off of that singularity, right? And so this freeness property where I can move any point on the curve in any which direction I want sort of, loses that meaning when I have a singular variety. Okay. Are we, please, I'm thankful for the questions, so please keep them coming. Okay, and so what's the major problem here? Sorry, problem. The problem is that the MMP involves singular varieties. So what the MMP does is it sort of takes my variety and tries to simplify it by a sequence of birational maps into a variety that's easier to understand, right? And when we do this, right, if you've seen this for surfaces, you might blow down -1 curves, right, and reduce the Picard rank of your surface. And in the surface case, you'll always obtain a smooth surface at the end of this. But in higher dimensions, this is not true. You might start with something that's smooth and end with something that's highly singular, right, but still normal, right? And so in this case, right, we really need to extend our study of varieties to singular fauna varieties, even if we hope to understand smooth varieties in the beginning, right? So the obvious question then is, do singular fauna varieties contain free rational curves? And so in the next moment, I want to sort of give you some examples of why we should think they do. And then some counterexamples to show that, there are some restrictions you need to put on the singularities of this fauna variety for this statement for you to hope the statement would be true. Okay. So let's do an example. Let X in P5 be the cone over a rational normal quartic curve. Right, so this means P1 embedded by O4, right? The complete linear system of degree 4 polynomials. Okay. So X here is, I want to give a small remark first. I want to describe to you or name some of the common singularity types that are going to come up in the MMP, in particular in this next example, right? So let me use this space on the whiteboard here. So MMP singularities. I mentioned that the MMP will introduce singularities to our variety. And so we have names for these depending on their type, right? There's varieties that are called terminal, right? Or that are said to have terminal singularities, canonical singularities, KLT singularities or Kawamata log terminal, or log canonical LC singularities. And so terminal singularities are sort of better than canonical or better than KLT or better than log canonical. In fact, there's strict inclusions, so between terminal canonical, KLT, and LC. So varieties get more singular if I say a variety has this type of singularities or is a KLT fauna variety, then it's an LC fauna variety as well, but it may not be a canonical fauna variety. Okay. So we'll just box this. Some useful terminology from that. KLT and LC. They're abbreviations because the words are a little bit longer. They stand for Kawamata log terminal and log canonical. You essentially put a log in front of the words and then pretend everything is the same. Okay, so let's return to our example. X is a cone over a rational normal quartic in P4, right? So X here is KLT fano. Okay. So it has pretty bad singularities, but not the worst, right? And it smooths to Y, which would be the Veronese of P2 into P5 given by the complete linear system of quadrics, right? Or conics on P2. Okay. Okay. And well, Y clearly has, free rational curves, right? It's smooth. It's a smooth Fano variety. In fact, Pn is the Fano variety, right? But what happens to these curves as I deform them, as I deform Y to X, right? How can we think about these curves, and how am I doing on top? Okay. Well, let's see what happens to lines first, maybe in Y. So lines in Y, well, Y is embedded via the system of conics. So lines in Y map to conics in P5, right? So lines in Y, which is isomorphic to P2, i.e. conics in the entirety of P5, right? Deform to the union of two lines in X through the vertex of the cone. Okay. So I'll draw a picture here. I have Y, which is just P2, and a line inside Y. And what happens is I specialize to X, which is maybe this cone over a quartic curve, is that this line will map to the union of two lines through the vertex of the cone. Okay. And you might look at that and say, but a line mapping to two lines, why is this true? Well, it's because the line corresponds to a conic in P5, right? And for degree reasons, this is the only thing that can happen, right? The base of this cone is a degree 4 curve. I can't have a degree 2 curve map onto a degree 4 curve. So it has to degenerate to a union of two fibers. Okay. But does this mean that, X doesn't have any free rational curves inside of it? No, we've just eliminated the possibility that, these lines in Y specialize to good free rational curves in X, right? And in fact, the next simplest example, right, conics in Y deform to hyperplane sections of X. And you see, right, that if I slice X via a hyperplane, I reobtain this rational normal curve that I took this cone over, right? And that is actually a free rational curve in X. Okay. So let's give another example, maybe, sort of generalizing this. So if I let XR be the cone over a rational normal curve in PR instead, then XR is log Fano. What I mean is it's essentially KLT. You need to put some log structure on it, include a boundary divisor. This is all fine. But every free rational curve in X has H degree at least R. Right. So H is the hyperplane section. Okay. And let's contrast this for a second with Kolar, Mori, and Miyaoka's result, right? These XR are all surfaces, right? Fano surfaces of some kind. But the minimal degree of a free rational curve in X is bounded below by R, right? And so what we see is that some result like Kolar-Mori and Miyaoka, which bounds the degree or the negative kx degree of a, of a free rational curve is hopeless if you don't constrain the singularities of the Fano variety even slightly, right? And let me give you a straight up counterexample to show that there are notions of Fano varieties that don't admit free rational curves in their smooth lookers.
The singularity.
Yeah, KLT. Yeah, so there's a boundary divisor that will make X a KLT log Fano pair. Thank you. The problem there being that the canonical or anti-canonical divisor on X in this construction isn't really Q-cardier. You need to subtract off some boundary divisor in order for it to become Q-cardier. Okay. So there are topological obstructions to having free curves of low degree like you would have in Kolar-Mori and Miyaoka's result. But also, if I don't suppose that my variety has KLT singularities, there are easy counterexamples that show it can never have free rational curves. So if I take X in P3 to be the cone over a smooth plane cubic, so the plane cubic will be an elliptic curve. Okay, so let me draw this cone here. Then X is LC Fano, right? But any C inside the smooth locus of X, a curve, right, maps to the elliptic curve. So any proper curve C inside the smooth locus of X will map down onto the elliptic curve and surject onto it, right, which is the base of X. And this in particular implies that C is not rational, right? C is not isomorphic to P1. Okay. And what this tells me, right, is that the only rational curves in X are the rulings of the cone, right? So in particular, X, by a definition of free rational curve, does not contain any free rational curves, right? Okay. The conjecture currently is that if you have a KLT Fano variety, then it will contain a free rational curve. That is not known. But let me give you some positive results. So I think this is the most appropriate to do on an Excel board. Huh? The lines, right? This is the sort of, if I blow up the cone point, this becomes a vector bundle over an elliptic curve, right? And the rulings of that, or this becomes a P1 bundle, sorry. The rulings of this P1 bundle are the only lines, the only rational curves in the variety. Okay.
Is it just three things or
Very free as well, yeah. I think free will imply very free, but that's my own. I just want to keep the notation simple. But yeah, good clarification. Okay, so far I've described the problem to you, and let me tell you what's previously known about it. So, sort of a landmark paper came from Keelan McKernan. They show that any KLT Fano surface contains very free rational curves. And so their proof is uses the birational geometry of these surfaces quite explicitly, and uses sort of like, classifications of KLT singularities for surfaces to sort of, manipulate the surface you have and obtain a free rational curve or obtain a rational curve in the smooth locus. And it's over 100 pages, quite detailed, and a very impressive result. Another result, also, it's difficult to know who to attribute this to, because I think, having spoken with at least Keel and McKernan, they reference that it's in Kolar, but then also the reference seems to be in their papers as well. So I'm going to attribute to both of them. So this is in the 90s, and Kolar or Keel and McKernan's result was in the 90s as well. They show that LCI terminal Fano threefolds contain free rational curves. So here, terminal, right, was the sort of simplest kind of singularities that we could have resulting from an MMP, right? And this LCI means local complete intersection, that every singularity at least is, can be modeled by a local complete intersection, spec of a local complete intersection ring, right? Okay. So these are actually the only known results about free rational curves on singular Fano varieties before our work. And there's some related constructions, right? Haken and McKernan, somewhere around 2007, showed that if you have a KLT Fano variety, then it's actually rationally connected, meaning that through any 2 points on the variety, I can find a rational curve that passes through both of them, right? But they can't show that this rational curve will miss the singular locus of the variety, right? And somehow, having that condition is really important when you want to study deformation theory of your varieties or come up with, boundedness results, which has been proven by BCHM. But just listing off a couple of the different consequences that having free rational curves would get you, right? So the question becomes like, how can we find curves missing the singular locus, right? And it's very difficult to answer because after the 90s, there hasn't been much progress, right? And so what if we tried to expand our approach and look for just nice curves in the smooth locus of any genus, right? What were the properties that I sort of alluded, or elided over here on this board when I told you that, this is what it means to be very free and they have great deformation properties, right? What were these properties about a free rational curve that made it so nice? And so I'll make the following definition, right? So definition, a non-constant map. What we're going to do is we're going to generalize free rational curve to free curve of any genus, okay? So a non-constant map, f from C from a curve into X, is an R-free curve if, so 1, you'll notice f of C lies in X smooth, the same condition as before. And 2, the pullback of the tangent bundle of X is globally generated and has, sorry, switched up a little bit here. And 2, for any effective divisor D subset C of degree R, the pullback of Tx twisted down by minus D is globally generated and has first homology equal to 0. Yeah. So again, I'll give you some nomenclature, right? if you just want free, right, this means again zero free. So free is equal to zero free again, and very free means one free or more, right? And so free reduces down to the condition that the pullback of the tangent bundle is globally generated and has vanishing first cohomology, right? Yeah. Yeah, let's let C be, yeah. Projective curve. Just keep, yeah.
Does this revert to this definition? C is
Yeah, because the point is that any divisor on P1 is rationally equivalent to any other fixed divisor of degree the same degree, right? So this condition that this bundle is globally generated is the same as saying if I twist down the pullback by minus r, I'll get a globally generated bundle, right? Which is the same as saying AI is greater than or equal to r for all I, right? And has H1 equal to 0. Well, that was implied by global generation on P1, but there are globally generated bundles on higher genus curves that don't have vanishing H1, right? Thank you for the question. Let me move over here. So why are these the right conditions? Okay. So for any curve C, right, to explain these conditions a little bit, I want to talk about the morphism scheme and its structure. So for any curve C, there's a morphism scheme, mor C into X, which sort of parameterizes all maps F from C to X, which are non-constant. Right. So this is actually a scheme. If you bound the degree with respect to some ample line bundle of your map, then it's going to be a quasi-projective scheme, right? And the tangent space of this scheme, so the tangent space at the point F, right, is x0, sorry, of the pullback of omega x mapping into O of C. Okay. And the obstruction space is just x1 of this. Okay. And when x is smooth around the curve, right, the pullback of omega x is, a vector bundle. Its dual is the tangent bundle. And so this will become just global sections of the pullback of your tangent bundle, right? Your deformation, your tangent space is global sections, and similarly, x1 will become h1 of your tangent bundle. Okay, and so this R free, insisting that if I twist down by a divisor D, is meant to capture that if I fix the image of a couple different points, I can still move the curve as much as I want, right? That's what it means for it to be R free in some ways. Okay, and so what's our main theorem? Go up to this board. So theorem. For, sorry, one page too far. Any KLT phono variety contains very free curves of some genus. So this is our main theorem. And some remark about this theorem is that cubic cones, or the cubic cone shows KLT is the best possible result here. So what we do is we change the problem from containment of a very free rational curve to just containment of any very free curve of any genus, right? And we see that, we can solve the conjecture once we remove the condition that the curve be rational, right? And the cubic cone shows it's the best possible, right? If I go back over to the cubic cone here, any curve in the smooth locus of this cone, the pullback of the tangent bundle, right? The tangent bundle of the cubic cone, if I take away the cone vertex, has a quotient down onto the tangent bundle of the elliptic curve, right? Which is a trivial vector bundle, right? And when I pull this back, I again get the trivial vector bundle on my curve, right? Which will always have H1 when the genus of my curve is larger than 0, right? So there are no free curves in this LC phono variety, right? There are just none, regardless of the genus. In fact, we show, that there exist R free curves for all R greater than or equal to 0, right? But we can also characterize LC phono varieties which contain free curves, or very free curves. So we express a condition on the LC phono variety in terms of its tangent bundle, which says it contains, a very free curve of some genus if and only if this tangent bundle has this property.
So what does it say, containing what?
Containing very free curves. Yeah, thank you. And so in the remainder of the time that I have, I want to talk about some applications, right? If you change the problem that you're answering, you should be able to apply it to some previous problems you cared about and still get, the solutions you want, right? And so let me go into that for the remainder of the time. So as the first application, I have the following theorem. So let X be a terminal phono variety. X contains very free rational curves if, and this chalk is getting a little small, let me maybe change, if either dim x is equal to 3, dim x is equal to 4, and x has LCIQ singularities. Okay, and these are slight generalizations of LCI singularities. You also allow quotient by a group action. Or if x is smoothable. Right. So this problem we were running to earlier, where it wasn't a priori clear that a phono variety who's smooth, that had a smoothing, as in this example, had free rational curves, we can show that if you bound the singularities to be terminal, indeed it does have very free rational curves. Okay, so we can answer the initial conjecture in many cases. Our second application is to fundamental groups. And so somewhere in the mid 2010s,
So that theorem says that in that three case, we have very free rational curves, but it can be other cases where they have, like, is it like only those three?
it's not only those three cases. No, we haven't disproven anything. We're just saying in these three cases, we can show.
Follow that, okay.
Okay. So our second application is to fundamental groups. So what's known about this, right? There's a lot that's already known about this. So it's known that fundamental groups of smooth fauna varieties are trivial, right? And more generally, it was expected for quite a while that if you had a KLT fauna variety, then its fundamental group was finite, right? And one strategy that people hope to use to prove this was sort of the analog of the strategy for smooth fauna varieties, right? The proof for smooth fauna varieties, you can find a way in which this follows from the existence of very free rational curves on those smooth fauna varieties, right? But there's this other fact that's known. So it's known that very free rational curves in X imply that the fundamental group of the smooth locus of X is finite, right? And so, if you're drinking the punch and believe that KLT fauna varieties should have very free rational curves, you should believe that KLT fauna varieties indeed have finite fundamental group, right? And in fact, this was proven by Braun in 2021, Lucas Braun in 2021. Right? And the methods used here were sort of the culmination of a decade sort of worth of investigation into these fundamental groups, into État fundamental groups. I used sort of induction on dimension, and didn't sort of follow this very free rational curves line of thinking, right? It's an incredible proof. So it's a little surprising, though, that we're able to recover this same result using just higher genus very free curves. So our theorem says that if X has higher genus free curves, so a free curve of genus at least one, right? Then pi1x is finite, right? So it's the same result as was known up here for very free rational curves, but just noticing that actually the proof strategy that you would use for very free rational curves implies the same thing if you just remove the rational condition. So in particular, as a corollary of our main theorem, we re-obtain Lucas's results through very different methods, right? Okay. And again, the cubic cone shows that KLT here for Lucas's result is the best possible, right? This cubic cone, when you remove the vertex, right, the fundamental group becomes the fundamental group of the elliptic curve, which is z plus z, right? But our result that also characterizes, LC fauna varieties containing very free curves implies that, we have a characterization that shows some of them as well have finite fundamental group. Okay. All right. And let me see what I'm going to flip up the order of these applications. So I want to get to one or two more things. What time does this end at? Does this end at 3:50? Does it end at 3:55? 4 o'clock?
I mean, before change.
Sorry. My apologies too. Yes.
This is a long time.
I don't have material for that. We're wrapping up right now.
Yes. up to 10 minutes more.
Okay.
We finish sometimes with the question, but.
I'll make it fast. I'll make it fast.
I mean, if it goes on before, yes.
So we also have an application to Mori theory. If you're not familiar with this, this is sort of what I mean by faunal varieties are combinatorial in a way, right? What Mori did, right, and how he related the geometry of faunal varieties to the rational curves they contain was through what's known as his cone theorem in some ways, right? So to state what the cone theorem is and tell you a little bit about it, I first need to introduce some notation. So for any variety X, we have the following vector space. So if I take the set of all curve classes, formal sums of curve classes, modulo numerical equivalence, so this means that modulo the relationship that they pair the same with any Cartier divisor, right? And then tensor this up with R over Z, right? And then I get a finite dimensional vector space called N1XR. Huh? Curve classes. Curve. Yeah, I blend my V's and my R's. I apologize. So inside of this vector space, we have so a cone of effective classes, right? So this means I want to take formal sums of curve classes with positive non-negative coefficients, right? I'm not allowing myself to subtract any class of a like closed subschema of X, right? And for an arbitrary variety, this effective cone can be very poorly behaved. You should take a closure in order to obtain a closed convex cone, right? But for a faunal variety, right, or more generally for any smooth variety, Mori showed the following. You can still make sense of the notion of an extreme ray. So let's pretend this cone, is nice and polyhedral for a second. An extreme ray of it is an edge of the cone, right? It's a facet of dimension 1, right? Or a face of dimension 1. Sorry, facet is codimension 1. It's a face of dimension 1. So what Mori showed in the 80s was that for smooth X, any kx negative extremal ray R inside this effective cone contains the class of C of a rational curve C inside X with anti-canonical degree less than or equal to dim X plus 1. So what's an example of this? Oops. What's an example of this? Pn, right, has just a one-dimensional space of curve classes modulo numerical equivalence, right? And the effective cone is, in R, it's all values of R greater than or equal to 0, right? Inside there, the extreme ray is, the cone itself, right? And the curve class lying on it is the class of a line, right? Which, if you compute the anti-canonical divisor for projective space, will have degree exactly dim X plus 1, right? So Mori's bound here was optimal. And it was conjectured that you should be able to say the same about a smooth, a faunal variety with, or a variety with some singularities as well, right? So Kawamata wrote a version of this in the 90s. So Kawamata said, if X is KLT, this implies almost the same thing, but with negative kx dot c less than or equal to 2 dim x. So he reobtained a bound on the anti-canonical degree of a curve representing this extreme ray. But it wasn't Maury's optimal bound below or above, right? And what both of these let you do is they sort of let you prove a cone theorem, right? That says if I have a KLT funnel variety, then every extreme ray of this effective cone is represented by a curve class of low degree, right? If I look at the set of all extreme rays, this is a finite possible set of all curve classes of this type. And so the cone actually has to be polyhedral, right? Which is very nice, right? But Kawamata's bound wasn't quite optimal. And this is what we're able to show. So we show that if X is LC, so log canonical, or in particular, it could be KLT. This includes all KLT varieties. And this implies exactly the same thing, but with negative KX dot C less than or equal to the original bound. Oh, means I should probably come and talk to you. So yeah, we improve Kawamata's bound from the same conjectured bound that came after Maury's result in the 80s. And so I think for time reasons, I will end here.